Welcome to Aerospace Structures. We'll be discussing the bolted joint and seal designs in lecture number 6. I am Vinay Goyal, and I'll be walking you through this lecture. Why we use bolted joints? We use bolted joints because they're non-permanent fasteners that allow us to quickly use it in the field. We can disassemble. It's easier to apply maintenance. And you can also make adjustments. Well, if you were to use a bonded joint or a weld design, you will not be able to disassemble as easily as with a bolted joint. And as a consequence, bolted joint does provide some advantages over these other more permanent joint designs. However, bolted joints do carry a disadvantage, and one of their disadvantage is weight. And so you ought to balance what are the benefits of going to a bonded design versus a bolted design versus a welded design, and determine what is the best course for your design. But typically bolted joints do offer advantages from the standpoint of maintenance, disassembly, and so forth. So it is very important to discuss the various standards, thread standards, and their definition. Here is an image that was taken from Shigley, and a lot of the presentation package that we'll be discussing today comes from multiple sources, and one of them is from the machine design book by Shigley. Here's an image of a thread. And I would like to discuss some of the terminology and jargon that is used in this area. The pitch basically is the distance between adjacent threads. The major diameter corresponds to the largest diameter of the thread. And you can see that that will be your major diameter. You also have the minor diameter, which is the smallest diameter of the thread, which goes from the root to root, and root is a definition that needs to be known. The crest is the peak, and the pitch diameter corresponds to the theoretical diameter between the major and minor diameters, where the tooth and the gap have the same width. Okay. We also have a chamfer here that sometimes is defined. We also have the thread angle, and this is usually is defined as alpha, or half of this total angle you see here. The American National Thread Standard defines basic thread geometry for uniformity and interchangeability. The American National Thread has two specs. You have the UN normal thread and UNR greater root radius. This one has a greater root radius for fatigue applications. We also have the metric thread, the M series, which is your normal thread, which is analogous to the American National Thread as UN. And then we have the MJ series, which is a greater root radius thread, again, great for fatigue applications. It is very important that as you're working through engineering problems, you select the right thread for your application, particularly if you're going to encounter fatigue applications such as in space applications. In those applications, it's very important to select the right kind of thread. Otherwise, you could get into an issue with early failures due to fatigue. And so UNR and MJ are the recommended approaches. We also have to discuss that Core Series UNC provides the ability for general assembly, frequent disassembly, but it may not be very good for vibrations. And that was discussed just earlier, that the UNF series tends to be the better choice for fatigue-driven environments, such as those where the sources are like good, like for example, the sources are vibrations or repetitive loading. You also, the UNF is used quite a bit in automotive and aircraft industry. The extra fine series UNEF are good for shock and lash vibrations. They tend to be high grade alloy, and they're used in aircraft. The basic profile for metric M and MNJ threads are shown in this figure, and they provide basic dimensions for standard threads, and typically have some of the dimensions are specified, and this data can be provided to you through tables and such or specs at different catalogs. Here is the diameters and areas for metric threads. You have the nominal major diameter, we have the pitch, which was discussed earlier, and for the coarse pitch series versus the fine pitch series, we will have information about the minor diameter area, the tensile stress area, and this information is provided to you so you can then make the right choice for which thread do you want. We also have diameters areas for unified screw threads, and we have size designation that goes along with them. And that's specified for core series UNC and fine series UNF. Again, we also provide the threads per inch, the threads per inch, and then we have the tensile stress area and the minor diameter area. The tensile stress area, AT, is really the area of the unthreaded rod with the same tensile strength as a threaded rod. So it is the effective area of a threaded rod, and this is the value that tends to be used for stress calculations. The diameter of this unthreaded rod is the average of the pitch diameter and the minor diameter of the threaded rod. And so it is very simple to calculate this tensile area based on this information, as typically this information is provided to you for that particular thread specification. There are other kinds of threads, such as square and Acme threads, and they're in these cases they're really intended to be transmitting power, and they'll be provided with information such as pitch and diameter, and in general, this information can be used then to these tables can be used to select your best option for your designs. So I want to go a little bit into power screws because the formulas for power screws actually will help us later when we discuss bolted joints in more detail. Power screws, well, we may not be using power screws in this class directly. I think by covering power screws, we will be able to tackle bolted joints, which are torqued into designs, and so we will be able to make progress from that perspective. So what is a power screw is really the idea, it provides you a mechanism or an approach to change angular motion into linear motion. And it usually will allow you to transmit power. Examples of these include vices, presses, jacks, and other applications. So really the question is, what is a torque required that I need to apply to raise or lower a load of some kind? We want to look at basically a thread at an inclined plane, and basically the static analysis. As you can see here, to lower or raise this load, it will be reacted by the nut F/2, by a value F/2 on either side. But when I look at a specific thread in an incline, what I really have is that force F is transmitted, and then I also have a tangential force, that's your frictional force, which could be minimized by applying lubricant, and they have a normal force acting against the surface against what we're threading against, as against the inclined plane. And so to raise or lower the load, uh, it will require a load that's acting in this direction to raise or to lower. You'll have that load acting on it in that plane. So all I have to do now, I have to just do static equilibrium for either the left option or the right option. Um, and when I do so, um, I can then write the two equilibrium equations for raising or lowering the load. And I'll find that to raise or to lower the load, I can solve for P, okay? And to raise the load, I have this P, and to lower the load, I have this P. We can divide this equation by cosine gamma, and when I do so, I'll quickly realize that that tangent gamma or lambda equals L divided by pi and the mean diameter. So tangent lambda is really the height L divided by pi dm. So clearly, I'm able to write everything in terms of the mean diameter and then the value L. And so these are geometric parameters are known. And so really the torque then becomes basically um, the force times the distance, the mean diameter divided by 2 times this formula. As you can see here, uh, this coefficient here is this one here. And this coefficient here is this one here. And so the torque is really P times the diameter dm divided by 2. And so that's how I get the value of torque. And so what we've done here is we've shown how torque relates to the force that we want to lift or to lower that load. So we have a relationship that depends on the geometry and the load that we want to lift or raise or lower. But in essence, what I'd like you to do is to pause the video and kind of derive these equations on your own and kind of go step by step and work it through. If lowering the torque is negative, the load will lower itself by causing the screw to spin without any external effort. And I think that's quite obvious. If the lowering of the torque is positive, then we have a self-locking condition. And the self-locking condition can be guaranteed using this formula, pi f dm greater than 1. And so that's important to realize, where F is the frictional coefficient or the frictional forces. Okay, and this is what it was discussed here, the frictional coefficient F. So there is a condition for frictional coefficient that can allow us to, with the correct mean diameter, provide us with a self-locking condition. We also note that L over pi dm is tangent lambda. So the self-locking condition can be seen to only involve the coefficient of friction and the lead angle. So again, we realize here very quickly that we can determine when self-locking condition can occur. The power screw efficiency is another calculation that can be performed, and it provides you the torque needed to raise a load with no frictional losses. And the efficiency, and that can be found by setting F equal to 0. And so then you can determine the efficiency of the power screw by dividing the torque with no friction by the torque for raising that load. And so that'll give you the efficiency of the power screw. Because friction is really what's causing things to become a little bit difficult in terms of raising or lowering the load. You can see here, if I set F equals 0, then dm and dm cancel, and then you have this condition here. Power screws with Acme threads will follow a very, very similar derivation, but what you're going to get now is the formula is a little different because of the geometry. The geometry is coming into play. And so the angle between the Acme incline thread is 2 alpha, and so half of that is alpha. And so then the incline is at an angle alpha. So you got F divided by cosine alpha for that component, and then you can derive this equation here. The friction component, the friction components are increased, and so it is important to understand that the formulas do differ, but they are derived in a very similar manner. Okay. Color friction is another important aspect, and it usually needs to be accounted for because you do have some amount of friction between the collar and the load. Okay. So assuming the load is concentrated at the mean collar diameter, which we could call this the mean collar diameter, then the torque component due to this friction is then the force, the frictional coefficient between the collar and the load, and then DC, which is the mean collar diameter divided by 2. Using statics of materials, we can determine the stresses in the body of power screws. The maximum normal shear stress in torsion of the screw body is tau equals 16 times the torque divided by pi diameter cubed. The actual stress in the screw body stress equals F over A. And then again, I can now put this in terms of the diameter of the screw. We also have to consider the bearing stress can be calculated by taking the force that's reacting on the power screw and dividing that by the area. And if we notice here, dm is the mean diameter, so we have pi and the circumference, which is pi dm, times p over 2, which is this distance here, times the number of threads. So that will give you the bearing stress reacted by n number of threads. It is very important to understand that in typical design, not all threads could be or will be engaged. And so it's important to understand that in many situations, we don't count on all the threads being engaged. So the less number of threads we put here in the denominator, the higher the stress will be. So we recommend typically not to fully account for all threads engaged because that may not be the case in real life. We can also calculate the bending stress at the root of the thread. And that calculation is simply the stress in bending M divided by the section modulus, which is really MC over I. You can see here Z is inertia divided by the distance C. And so we really have MC over I, but this is another way to look at that. The bending in this case is the force F times P divided by 4, because we have at the root, you have this force, this distance P over 2, and so this distance here is P over 4. So that's your moment. And we're trying to get the moment, the bending stress about the root, okay? And so in this case, we also have to consider what is the inertia for our situation, and that's the inertia of this piece, and that can be calculated with this formula given here. Um, and so then the bending stress will be equal to 6 times the force divided by pi dr, the number of threads engaged, times P. The transverse shear stress at the center of the root of the thread is really the shear force V, which is the same as F, and the area can be calculated as the circumference times P over 2 times the number of threads engaged. Again, if we assume NT to be lower, because maybe not all threads will be engaged, this shear stress will shoot up. Now remember that this is 3 over 2 because the max stress occurs because there's a parabolic distribution uh, from the top to bottom. So the highest stress tends to be in the center, and that will have a factor of 3 over 2. So the next step then is here's a set of stress at the top of the root plane. And so we calculated this stress, this stress, this stress. And so what we need to determine now is what is equivalent von Mises stress due to all these stresses acting on the thread. And so we can use the von Mises equation here at the bottom by substituting all these quantities that were derived just right now, and then perform the final calculations. So it is important to understand that thread deformation and screw knot combinations need to be understood. A power screw thread is in compression and will cause elastic shortening of the screw thread pitch. We will engage the nut and it will be in tension, causing elastic lengthening of the nut thread pitch. Consequently, the engaged threads may not be equally sharing the load. Typically, it has been found that the first thread carries 38% of the load, the second thread carries 25% of the load, the third thread carries 18% of the load, and when you go to thread number 7, you may be free of load. And so to find the largest stress in the first thread, we recommend using 0.38 F in place of F, and then setting NT equals 1. In other words, you either use F with an NT of 3, which is basically saying that only 3 threads are engaged, or just look at the largest stress in the first thread, which experiments have determined is in the order of 40%. So that's kind of what we discussed earlier. We don't want to really count on all the threads engaged. So here's an example that could be discussed in great detail, but for now, what I want to do is to kind of describe what the question is, and I don't want to solve it now, but have you go through that on your own and work it through, because it's essentially using the formulas that we had discussed. A square thread power screw has a major diameter of 32 millimeters and a pitch diameter of 4 millimeters with double threads. And it will be used in an application like this. We're assuming a friction coefficient of the color of 0.08, a diameter of 40 millimeters, and a force of 6.4 kilonewtons per screw. That's the load that we may raise or lower. So what they're asking us to do is to find the thread depth, the thread width, the pitch diameter, the minor diameter, and the lead. And I think you all know where this goes with A. B is finding the torque required to raise or lower the load. C is the efficiency of the lifting load. D is finding the body stresses. E is to find the bearing stresses. F is to find the thread bending stress at the root of the thread. G is to determine the von Mises stress at the root of the thread. And H is to determine the maximum shear stress at the root of the thread. And so I don't want to go step by step and answer each of these, but what I say is that we can determine the different values for part A just looking at this figure. And then determine what is P, what is P over 2, and so forth. And then once we have that information, we're ready to enter that into your torque to raise or torque to lower. All this information for F was given to you as 0.08, the friction coefficient. We know D, we know F. So all this stuff should be very easy to calculate. And the main thing to focus here is that we can see here clearly that to lower the load, the torque required is less. And that makes total sense. You can see that working out. And to raise the load, the torque required is higher. So everything matches really well. You can see that it works really well. And here what we've done is we've added the torque from the collar. So that has been added, which was not shown before, but the torque required is going to have to account for the frictional coefficient between the load and the collar. And so that's what was done here. And then you can actually calculate efficiency by assuming a friction coefficient of 0 for the numerator, and then divide that by the torque to raise. And this shows you that the overall efficiency in raising the load is about 30%. You can then use the calculations that we just discussed to calculate the body shear stress, the bearing stress, the thread root bending stress sigma b, the transfer shear stress. And once you have all these values, you're ready to plug that into your von Mises stress calculation. And then that can be compared against the allowable of the material. So there are various ways of going about this, but bottom line, you will get the same answer if you were to use the principal stresses and then use the von Mises stress. So I want to move on here a little bit into power screw safe bearing pressure. So there are some materials provided, the nut material, and what is a kind of safe bearing pressure that is good. So that's something that people consider in design. Power screw friction coefficients are useful. They come from various sources. Again, these notes came from Shigley, but it provides you frictional coefficients between various materials, and that is what is nice about looking at this carefully. I do want to consider and talk about head type of bolts. There are various head type of bolts. Hexagonal head bolts usually will use a nut and is heavy duty. Hexagonal head cap screw is a thinner head, and so it's often used as a screw. You also have socket head cap screw, usually used more for precision applications, and it allows you access from the top. Machine screws are usually smaller in sizes and are threaded all the way. Anyway, so I wanted to provide a little bit of some insights into the kinds of machine screws you could have, such as round head, Philister head, truss head, and so forth. So there's many kinds. Focusing on the hexagon head bolt, those are one of the most common in engineering applications. And the standard dimensions are included, or they're typically provided in the Shigley's book as an example, table A29. The width tends to be about, the width of the head tends to be 1.5 times the nominal diameter of the screw. The bolt length is measured from below the head, so from this point downwards. I want to talk about a little bit about the threaded lengths, and knowing this information, I want to point out that this length can be found. Given the diameter, we can then determine for different lengths what is the threaded length. And so these are very standardized and can be found with these formulas. You can find specific typical applications, typical specifications in Appendix A31 of Shigley. The first three threads of the nut carry the majority of the load. We discussed that already. Localized plastic strain in the first thread is likely, so you should not be using nuts and reusing them, because if you do so, then the other threads that are not plastically deformed will have to take all that load, and then slowly you may not have a very effective nut. Here you can see a washer face regular, a chamfered both sides regular, a washer face jam nut, and chamfered both sides. And so these are very typical nuts that you may find. I want to discuss a little bit about tension loaded bolts. That's very important to us. Um, we have a load applied to the joint, but we want to make sure that we have sufficient preload on the bolt to compress the members. The washer underneath the bolt head, what it does, it prevents bearing of this corner of this member onto the bolt. And so, again, there's various things going on here. The important thing is that bolts are really intended to, tension loaded bolts are intended to compress the members and decrease the amount of bending that you may have in the system. Otherwise, if you have gapping, then the bolt has lost its purpose in this situation, which is to join two members together. Here's an example of a bolt with an O-ring, and O-rings are extremely important for sealing applications. So you may have a pressure inside this vessel, and the pressure is acting to separate the flange from the wall of this valve, as an example. You may have a bolt in here that's preloaded to apply compression to then compress this O-ring and not allow leakage of this fluid to the outside. You'll be doing an analysis to replicate this condition. One of the things we need to consider is the O-ring. We don't want to damage the O-ring by compressing it too much. The groove design should be selected based on standard groove designs that go along with the O-ring. We want to make sure that when thermal conditions are applied, that the O-ring does not shrink too much or becomes ineffective, such as the case as a Challenger, where the O-ring was not effective. We want to make sure that if you have primary and secondary O-rings, if we have a design problem, you understand that the design problem that occurred on the primary O-ring will also apply to the secondary O-ring. And these O-rings, the secondary O-ring, which should act as a redundant O-ring, may in fact may not be effective as well. And so it's important to understand that your analysis should consider all combinations of things that could go wrong in terms of tolerances, thermal conditions, pressure conditions, preload, making sure that preload is maintained during the application. Here's more information about the screw in tapped hole. The effective grip length, again, is provided and is standardized, where T2 is the thickness of your second plate, and then H is the distance between the washer and the first plate. So then you can use these formulas to calculate the effective grip length, which will start at the bolt head, okay, all the way down here. So how to calculate bolt joint stiffness? That's very important to really understand what is going on with the design. I want to go back a little bit and make sure we understand the effective grip length. So the effective grip length is going to be important because that connects the plate here and the plate here, okay? And so going back here, the bolt joint stiffness becomes very important. Why? During preload, the bolt is stretched, the members in the grip are compressed. When external loads are applied, the bolt will stretch, members in the grip will compress some. So it's important to really understand how the bolt can be modeled effectively. As you can see here, you have a threaded portion, you have the unthreaded portion. So what you can do is you represent this as stiffness K1, stiffness K2, and then treat these as parallel, two springs in series, sorry. And if you do that, the effective spring stiffness of this bolt is going to be K1, K2 divided by K1 plus K2, where K is basically EA over L. E is the Young modulus, A is the tensile area divided by LT, which is the grip length, and then you have um, the unthreaded portion, which is the length that doesn't have any threads, and that's AD times E divided by LD, and I can calculate the bolt effective stiffness from that. I apologize for that. Then we have, given the fastener diameter D and the pitch P, we can determine the grip length. We can. And if I know the nut thickness H, the washer thickness T, then I should be able to calculate the bolt stiffness fairly easily. And again, for the English series versus the metric series, the grip lengths or the threaded length can be determined, and which it is part of the calculation. Okay. The fastener length is also important, but that can be found from the specs. So in general, then the fastener stiffness is AD times AT times E divided by AD times LT plus AT times LD. So these are calculations that should be used in the calculations. These are the areas of the threaded portion versus the unthreaded portion. So there is an understanding that when you apply a bolt preload, that there is a stress distribution, and that stress distribution will spread from the face of the bolt in the form of a cone. This may not be look like a cone, but it could be idealized as such. So we call this a frustrum. Anytime you're looking at a cone with the top cut off, and you can see here it's cut off. It's not a cone that emanates from a point, but it is a frustrum instead. So there's been a lot of research in trying to figure out what is the stress distribution, and what people have reconciled is that it's most likely a conical frustrum, and that's based on ultrasonic techniques. People have shown that researchers have shown that the conical frustrum is a good approach. The oval donut is an approach that people have used. Finite elements will definitely be the approach that's the most effective and maybe not as efficient. But for hand calculations, the conical frustrum is the gold standard in this kind of analysis. So models to calculate the member stiffness, because we covered how the bolt stiffness is determined, but now we want to cover how the member stiffness is determined, which plays a role in the bolted joint design. We want to model the compressed members as if they're frustra, spreading from the bolt head, from this location, and nut to the midpoint of the grip. And so what we want to do is use a frustrum as a half apex angle alpha, and then find the stiffness for the frustrum in compression. So here, as an example, I have the top part, the top member that will be bolted into the part. And if the grip, total grip is L, so L divided by 2 is the midpoint. I want to draw a frustra, okay? And that frustra is going to have an angle alpha, okay, with a diameter d. And so what I want to do is find the stiffness due to this frustrum in compression. So one can do a very elaborate calculation on what that will look like by basically finding the overall deflection of this frustra. We know the modulus is E, the load is P, but and since a conical frustrum, you'll have a pi, this integral through a thickness. So if all this formulation, you'll have to go through all this calculation, but at the end of the day, get the stiffness is pi, the modulus E, D, tangent alpha, and alpha is half of the apex angle of that frustrum. You also have this large D, which tends to be about 1.5. It can be about 1.5 diameters of D, 1.5 D, sometimes is one approximation people make. And then you also have the thickness T that should be considered. That's this thickness here of that plate. And so you can get the member stiffness K using this formula, and that's a log, natural log here. The typical value for alpha people have found is 30 degrees. So that makes it easy to plug into this equation and further simplify the problem. So that will take care of all this tangent alpha. If you have multiple frustras, you will have to combine them in springs in series and then calculate a total stiffness for that joint. Recall that I just told you the large D is about 1.5 D, so that's what you'll plug in there. And in essence, you will then do the calculation very quickly. These are to show you that finite element models tend to agree with the frustrum model. I won't go into great detail, but in general, the finite element models do a great job with this type of approach. There are exponential curve fits in finite element results that can be used for common materials within the grip. People have used this successfully for various materials and then be able to then use A and B to calculate a member stiffness with great success. Here's an example of two plates that are clamped by a washer. And they provide you the UNF, bolt, grade, and the plain washer material, steel. The question is, what is KM? If these two materials are, this is steel and this is cast iron, they want us to use the conical frustra equation, and then they want us to compare it with other approaches. And they also want us to determine the bolt spring rate. So the first step is to realize that when I look at this is only half, this is about 3/4. But in essence, where is a halfway point is about here, okay? So what I want to do, I want to be able to account for the washer as well as part of the member stiffness. And so what I want to do is calculate the frustrum now for this system here. Now realize that this piece of the frustrum overlays on the steel. The bottom one here, this frustrum in red, is now on the iron, cast iron, and then you have this bottom frustrum, which is in the cast iron as well. So we found what's our halfway point into the joint, so that's important consideration. And now I'll focus on the top frustrum, and all I have to do here is to calculate, I know this distance here is 1.437. This distance here is 0.75 is given to us. I know this is 1.437 because we told you that the frustrum is going to have a 30-degree apex angle. And so you can then calculate what this distance should be, okay? Pure geometry. Um, and so I can now substitute all the information in here. The diameter that goes here is 1.5 times the diameter of the bolt. So that's 0.75. So we have all the information to plug in. Steel is about 30 E6 in modulus. We're going to use the 30-degree tangent 30 degrees as part of the calculation, as explained earlier. It is a good approximation. And then I can calculate, using this formula, I can calculate K1 for the first frustrum. And I invite you to pause the video and see if you can use this formula successfully and then apply for our situation. Now that I give you a second, I hope you paused the video and did the calculation. And if you did it correctly, congratulations, you're the king of this bolt today. Good job. If I continue now for the second frustrum, here's the second frustrum we're talking about here. And that second frustrum, the distance now is 0.0775. That's your thickness here that goes in here. And then I have this distance 1.437, and I still have the 0.5. So I want to use this formula, and I get a K2 for that cast iron. And the cast iron has a modulus that's different from what you from the steel. Then I go to the bottom frustrum and repeat the calculation. And when I do so, I get a K3 of 14.15. So then I can put the springs in series, add them up to get a total member stiffness of 9.378 E6 pound-force times inch. I could then look at the entirety. Like if I were to assume the whole thing is steel, then I will get a calculation 14.64. And then if I want to compare that with the finite element approaches that people have used, you'll find a very similar answer. But note that this answer is quite different from having everything steel, but it's very close to the finite element approximations. Just recommended to use that. For finding the bolt stiffness, 2 springs in series, in essence, we can quickly do the calculations to calculate it using the threaded and unthreaded portion of the bolt, and then we'll get this number here. Okay. And again, feel free to pause the video and do it on your own to kind of see if you get the same answer. So bolt materials, and I'll explain later how this information is used later, but grade materials will specify heat treatment strengths, and the grades will typically be marked on the head of the bolt. I want to point a few things here. With bolts, it's good to, if you have a lot of bolts, it's good to test one of that lot to make sure that the lot is good. There's nothing going on from the process perspective. But there are things that should be considered here. The proof load is a maximum load that a bolt can withstand without acquiring a permanent set. Here, proof load is not the same thing as proof testing a bolt in the sense of making sure the proof has good workmanship. Proof load really means that it's a maximum load a bolt can take without having any permanent elastic deformation. Then we have something called the proof strength. The proof strength is the ratio of proof load and tensile area. So divide this load by the tensile area, and that's going to give you the proof strength. Typically, that corresponds to the proportional limit, and it's typically lower than the yield strength. And good materials, good bolt materials, will have a stress strain curve that continue to rise to fracture. And that's great because if you have an issue, you have some amount of ductility that protects you against brittle failure modes. Here are some SAE specification for steel bolts. You can see here the markings on the head. You can see here it provides you the yield, tensile, and proof strengths that allow you to size the design. And notice here there's a bottom Note here that says minimum strengths are strengths exceeded by 99% of this fastener. So these values are statistical in nature and provide a good confidence for design purposes. ASTM specification for steel bolts will have different markings, but very similar information such as proof strength, tensile strength, yield strength, and the material involved, and then will give you the size ranges for the various types of designations. We also have the metric mechanical property classes for steel. Property classes provided, the proof strength, tensile, and yield strengths are provided for the various types of materials with a head marking of some kind that will correspond to that property class. Here's more additional information on bolt specifications. Typically, we'll have information on nominal diameter, the threads per inch, the length, the thread series, the class fit, the material grade, and the head type. You may find also metric information, pitch, material class, and so forth. So I want to move a little bit more into the mechanics of tension-loaded bolted joints. We have a preload that I'm going to specify as FI. So that bolt has a preload. P total is a total external tensile load applied to the joint. Now it's very clear that total external tensile load applied to the joint some of that load will be taken by the bolt, some of that load will be taken by the members. So per bolt, I will have a load P, some of that goes into the bolt, some of that goes to the members. So P total is basically P times the number of bolts I may have. So again, however, it is important to realize that that's the external load applied. Some of that goes into the bolt, some of that goes into the member. But when I look at the resultant bolt load, what I really have is a load taken by the bolt, but I have to add that to the preload because the preload has that bolt into tension. So that's really the resultant bolt load that should be considered. For the member, however, because the member is in compression, it will decrease the force, the resultant force on the member. So you have the load P that goes into the member, PM, minus the preload, that gives the resultant load on the member. So these two quantities are very important. So then C becomes the fraction of the external load P carried by the bolt, while 1 minus C gives you the fraction of the external load carried by the members. And P times capital N provides you a total load that the joint can take. So during the bolt preload, the bolt is stretched. The members are compressed. And so we can use this formula. This formula provides me, if I know Km and Kb, the member stiffness and the bolt stiffness, I can tell you how much of that load externally went into the member and into the bolt. So this information is very important. That's why we had to do that calculation earlier, is to show you that by finding Km and finding Kb, I can determine what percentage goes into the bolt versus the member. And recall that Pm plus Pb is the total load applied P. So if that's the case, if P is Pb plus Pm, then basically the force that goes into the bolt is Kb times P divided by Kb plus Km. And note that I know all these values. These are the bolt stiffness, the member stiffness, which I showed you how to calculate using the frustum approach. P is the load applied to the bolt, to the joint, I'm sorry. And Pb becomes the amount that goes into the bolt. This coefficient here can be called C, and that's a fraction basically of the total load P that goes into the bolt. C is also defined as the stiffness constant of the joint. So this C. Pm must be P minus Pb because Pm plus Pb equals to the force applied to the joint. I can factor out P, so I get 1 minus C times P. And so C indicates the portion of the external load P that the bolt will carry. A good design target is to have C to be close to 0.2. That's really a good design target. And you can see here for various bolt grips, what kinds of values of C you can find. Okay. But again, C gives you what is the proportion of the external load P that the bolt will carry, and we want to see that being about 20%. Because, of course, we have preload, so we don't want to take too much load into the preload. We want to drive most of the load into the members. The resultant bolt load then is PB plus the preload. And PB came from the external load P, but some of that goes into the bolt, some of that goes into the member. And here for the resultant bolt, we have the basically the stiffness constant of the joint C, which is this ratio here that's known, times P plus Fi. And the resultant load on the members is this one here, is the force that goes into the member minus Fi, which is a preload, 1 minus C times P minus Fi. And we want to make sure that the member is in compression. If it's not in compression, then we have gapping. Otherwise, we have a situation and the preload may be insufficient, or the bolt is not, or the design is not working properly. So we definitely need the members in compression for this to work. There are some issues related to bolt torque, to bolt tension. The best way to measure bolt preload is by relating bolt elongation to calculated stiffness. But bolt elongation measurement is not practical. Measuring the applied torque is common using a torque wrench. So we need to really find a relationship between applied torque and bolt preload. That's a standard definition. And as you know earlier, I told you we're going to discuss power screws, and part of the reason I wanted to do that is to basically develop this relationship of bolt torque to bolt tension. And one can use all these formulas that I had discussed earlier, but I want to really simplify that to a very simple equation. That's torque equals K, the nut factor, times the preload times D, the diameter of the bolt. So while I discussed all this stuff earlier, I want to simplify the formula to this equation here, because K is typically really somewhere between 0.1 and 0.3, depending upon what you have. Typically, you want to use 0.2 for all other cases if you don't have the data, but K of 0.2 is a good guess in this relationship that's being used. I want to point out a few things here, is that the preload can vary substantially. But when you apply lubricant to the same samples, the standard deviations will decrease quite a bit. And so lubrication will make very little difference on the average preload versus torque. And you can see here the average is 34.18 kilonewtons. Here is 34.3 kilonewtons, but the standard deviation has been greatly decreased by half or so because we added lubrication. And so lubrication really helps with achieving a design, a bolted joint design that provides you more predictable torques. So here's an example that we could go through and talks about how to determine the preload for the problem at hand, to determine the torque necessary to develop that preload, and also to determine that for friction coefficient 0.15. So I invite you again to pause the video, go through the calculations if you can, but we can calculate preload stress very simply. Fi is 25 as the preload was given to us, and the area, tensile area can be calculated as simply as 0.373 based on the table of specs. The stiffness constant can be quickly determined as 0.32 because the member stiffness were given to you, so you can calculate C. Once you have that, you can calculate the stress under the service load that's provided on the bolt. So the bolt stress is going to be the C times P, and P is going to be the load of 6 kips that's applied to each bolt. So you have 6 times C plus the preload divided by the area gives you the stress of that acting on that bolt. The minimum proof strength is 85. And so we can see here that it's lower than 85. We can calculate the torque necessary. You can use a value of K that's 0.2 as one option, and that's what's done here. And that will give you the preload, the torque necessary to achieve the preload that has been specified. You can see here by using a more complicated formula, you get a very similar value as the one here at the top. You can also calculate factors of safety, axial stress, yield factor safety, load factor safety. But the joint separation factor safety is very important. You calculate preload, the constant of that joint, the external load applied P. We want to make sure that there's no gapping. It really comes down to this equation. We want to make sure the member, this member is in compression. If it's not in compression, you will have gapping. So that is the criteria that should be considered in the design. Also, we recommend that the preload be about 0.75 times the proof load or 0.90 proof load for permanent connections. For non-permanent connections where you're going to have to have some reuse, then you want to use 0.75 times the proof load. And the proof load can be found by the tensile area times the proof strength. So, so I hope that this is quite clear. We can apply that now to another example where we have these two materials. We could have a potential O-ring included. And so the question is, I have end bolts. They're used to resist a separating force of 36 kips. So what we want to find is KB, KM, and C, and then find the number of bolts required for a load factor of 2 where the bolts may be reused and the joints may be taken apart. With the number of bolts obtained in part B, we want to find the load factor for overload, the yield factor safety, and the load factor for joint separation. So this should be a very simple problem to go through because we've already covered all the concepts behind that. So why don't take a time to pause the video again and kind of see if you can get there on your own. And instead of now that you've paused the video and gone through the whole problem and solved it, I'll show you the answer, and perhaps you can compare against what you got, but you can find the bolt stiffness very readily using the formulas that we discussed before. We can then find using the conical frustrum equations or even using the finite element equations, and you can see that KM becomes very close to each other, either the FEA approach or the standard equations we had previously discussed with a 30-degree apex angle. And you can use this information to calculate C, or the stiffness constant of the joint. Once you have that, you can then now look at the preload that's recommended for disassemblies or reuse. So that's 0.75 times SP times AT. That'll give me 14.4. Once I have that, I can find a relationship that tells me what is NL, or the number of bolts, basically. So you will find that you'll get about 6 bolts when you run through the calculations. And by the way, NL is more of a factor of safety. I apologize. NL is 2 for our situation, and then you can calculate N from this equation. And remember, P total divided by N is P, which is the external load applied to a joint per single bolt. And then you can just use these equations very simply to find big N, which is about 6. You can actually recalculate with 6 bolts what is the actual factor of safety. That's 2.18. You can calculate yield factor safety and then load factor safety to guard against joint separation. And so this example really walks you through a number of challenges that are quickly resolved by using just the formulas we had discussed earlier in the lecture. I'll now move into gasket joints. What you really want to do is gasket joints also provide a way of sealing. And so full gasket joints are compressed between members of a bolted joint, and the gasket pressure P can be found by finding the force, dividing the force in the member by the gasket area per bolt. The force in the member then can be found using the very same formula we discussed earlier, and so then the gasket pressure that needs to be applied is this much. And so really it comes down to making sure that the gasket pressure is sufficient to prevent a leak. So you want to keep the members in compression. That really is very important for us for these kind of applications. And AG is a gasket area per bolt, and FM is a force that's acting on that member, as discussed earlier. Uniformity of pressure on the gasket is important. Adjacent bolts should not be more than 6 nominal diameters apart on the bolt circle. For wrench clearance, bolts should be at least 3 diameters apart. And so that will give you a good rule of thumb for bolt spacing around a bolt circle of diameter dB. Let's look at the failure modes that you could get when you're using bolted and riveted joints. And so the shear loaded joints are of extreme importance. And this case is called a single lap joint. This is connected by a single bolt. And as you apply loading to this scenario, you're going to have some amount of bending. And that's because of the eccentricity of the load relative to the thickness of this part. And so that will cause some bending of the section. You also have the situation where as you apply loading, it's possible that the bending will be significant enough where you could start yielding the bolt. So that's one failure mode that needs to be watched out for, because the more yielding you have, the more the potential for bending, and the joint could have some issues retaining its stability for bending. We also have a situation for shear bolt. You could have a shearing of that bolt. You can have membrane, or the members will fail in tension. You could also have the situation where the bolt pushes on the hole and causes a crushing type failure mode, causing, and we call this a bearing stress on the member. We also have a situation of shear tear out and tensile tear out. So 2 additional failure modes that need to be considered. The failure by bending can be approximated by determining the forces applied to this single lap joint, and then we can multiply that by the thickness. Sorry about that. The force times the thickness, the grip length, divided by 2. And typically the grip length T is the total thickness of the connected parts. The bending stress is determined by regular mechanics. So we basically have stress equals MC over I. And we will write it in this manner, M divided by I over C, because what we're looking for is the lowest value of I over C that corresponds to either the member or the bolts that are attaching the members. We also have the simple failure of a shear bolt, which is essentially shear stress equals the force applied divided by the area, and that area can be the threaded area as an example. We want to use the total cross-sectional area of the bolts to determine this shear stress per bolt. Simple tensile failure mode occurs in the membrane, and what needs to be considered here is the stress concentrations can be a problem. You can also have the free edge being a problem when they're near a hole. But in essence, what we want to do is calculate the stress due to the high stress due to any stress concentrations. In a simplistic manner, the net area of this member is basically used in the stress calculations, but typically this will be amplified by any stress concentrations. To determine these kind of amplifications, we recommend looking at the Peterson's stress concentration book. We also have the Rourke's stress formula handbook. Failure by bearing stress is essentially crushing of the material under compression. And so the bolt or member with the lowest strength will crush first. You can determine the load distribution due to this cylindrical surface being contacted by the bolt. While it's non-trivial, what is recommended typically is to assume a uniform distribution of how that bolt is in contact with the hole. And so that projected contact area is assumed to be close to A equals the thickness of the member times the D, which is the diameter of the bolt, and then that will give you the stress for the member. Edge shear out and tear out can be avoided by spacing the bolts at least 1.5 diameters away from the edge. Here's a quick example where we're trying to take cold splice plates and then use some bolts to attach them. Here we have 4 bolts. We have the splice plates here, and then they're connected by the butt splice plates. Are steel bars are connected by the cold rolled splice plates. And so we want to then analyze for a design factor of safety of 1.5, the static load that can be applied that can carry this load by the bolts. So we can determine the minimum strengths that correspond to the members, and then we can determine minimum strengths that will correspond to the bolt. The strength information can be found in MMPDS, typically for aerospace applications, and bolt data is typically provided by the suppliers or can be found through online sources. We realize here that by applying a force F, we have realized that the force applies F, about half of that is transmitted by each of the splice plates. Okay. And so we can then calculate the bearing and bolts, and the bearing and bolts is definitely F divided by 2 times the thickness of the plate times D. And you can see here that I need to make sure that this does not exceed the proof strength of the bolt divided by the factor of safety. And we say it will be 1.5. Here we have selected, we can solve now for F, so that F equals 2D times the proof strength divided by ND. The factor of safety is 1.5, 2 times 1 inch, because we're looking at the 1 inch plate here. And then we have 3/4 for the diameter, and then 85 from the spec of that bolt, the proof strength. So that'll give you 85 kips for that force. We also have bearing in members that should be calculated. So we have the force that's applied divided by 2dt. And we want to make sure that it doesn't exceed the yield strength of the material. As a consequence, we have yield strength divided by the factor of safety. We can solve for F. And as we go through this calculation, we found that F equals 54 kips. We continue the calculation. So the shear of the bolt it can be a problem. So if we assume that all bolts are active and they're carrying about the same load, then we can then take F, the force F, divided by the 4 bolts times the cross-sectional area, and equate that to the 0.577 times the proof strength. So the tensile strength has been converted into shear strength divided by the factor of safety. Solving for F, we again find a value of 57.8 kips. We can also look at whether the threads do extend into the shear plane, and if it does, the area will be smaller than what was considered in the previous calculation. So in this case, the thread did not extend into the shear plane, but in this case it does. And if it does, the force calculation will be reduced because the threads do cause the bolt to fail a little bit earlier due to the stress concentrations at the root of the bolt. We can then calculate edge shearing of a member at two margin bolts. In this figure, we want to make sure that the force divided by 4 times AT equals, and here we use the shear transformation from tensile to shear with a factor safety of 1.5. Solving for F again, we have 4 A's provided, which is the distance to the edge, and it's provided here. You can do a calculation to figure out the edge to that edge of that plate. And that's 1.125 times 1, which is the thickness of the plate, times 0.577 times 54. So we get a force of 93.5 kips. Tensile yielding of members across the bolt holes can also be calculated. And so that will be equal to the force equals times that will be equal to 90 kip. And then we can make sure that the member doesn't yield. And so we realize really that the limiting value of the force is the bolt shear. So 45.9 kips is the maximum force that we should be applying to this joint, assuming that the threads go into that shear plane. However, it is not common to have the threads to go into the shear plane because that's a poor design. We don't want that. So assuming a good design, we will then calculate the bolt shear based on the threads not extending into the shear plane. And in that case, we get that the bolt force is 57.8, or the applied force is 57.8, so we don't fail a bolt. So therefore, bearing stress is really limiting quantity here, here at 54 kips. And so that's the maximum load that this joint can take, based on the information we have discussed. So let's talk a little bit about shear joints with eccentric loading. Eccentric loading is a situation when the loads do not pass along the line of symmetry of the fasteners. It requires finding the moment about the centroid of the bolt pattern and the centroid location. Okay, so given the locations of the bolt pattern, the bolts, and the pattern that I have, I can determine the moment about the centroid of the bolt pattern. And so it's important to find the centroid location for this pattern of bolts. And A here can be the cross-sectional area of the bolt, and X can be distance to an arbitrary axis that defines the location from the bolt to the y-axis. And so here's how you calculate the centroid for such situation. So shear joints with eccentric loading should be considered. And here's an example of eccentric loading. We also need to construct the free body diagram to really tackle this problem and to really consider the bolt pattern appropriately in the calculations. We can then calculate the primary shear and the secondary shear due to the moment load applied around the centroid. I'll go into some calculations to show you how this can be applied in a simple way. So here we have a plate that is subject to a shear load of 16 kilonewtons. And as you can see here, this 16 kilonewtons is going to be reacted by these 4 bolts equally. And this 16 kilonewtons will be reacted about 4 kilonewtons each here. But this also causes a moment that about the point O is really 16 times 300 plus 50 plus 75, which will give me a total of 6,800 newtons per meter. And so visually looking at that, the 16 kilonewtons is getting reacted by these forces here, 1, 2, 3, and 4, about the same magnitude, 4 kilonewtons. But you also have this moment. This moment is also causing a force in each of these bolts in this direction, perpendicular to the radial direction. And so as you can see here, this distance is 96. It can be calculated to be 96. So you'll expect that this force times this radius equals this moment. But you have 4 of this. And so as a consequence, you basically have force times 4 of them times the radius equals the moment. So that will give me a force of about 17.7 kilonewtons that reacts that moment. Okay. So in going back to this diagram, we have found that this force is 17.7, the one caused by this moment. So that force acts in this manner. Okay. And then you have the forces from the shear, which are about 4. So that will allow you to find these resultants FA, FB, FC, and FD. What you'll find is that FA and FB will give you about 21, while FC and FD will give you about 14.8 kilonewtons. So we'll use a larger number to calculate it, to calculate the shear stress. And you could, again, assume whether it's threaded versus unthreaded going through a shear plane. But you can fairly do a calculation using the area of the bolt. So with that information, we can get that tau is 146 megapascals. You can also look at the bearing stress due to this bolt acting on this part. And so since AB equals T times D, the thickness being 10 and the diameter being 16, you can calculate the bearing stress as 131 megapascals. Another example is, say you have a pattern of bolts that looks like this. Fastener 1, 2, and 3. I apply a load of 1,000 pounds at this location. So the first step really is to find the centroids of this bolt system. So the X coordinate can be found, the Y coordinate can be found very simply. And so for each of the bolt or fasteners, assuming that each of these guys, fasteners, have the same cross-sectional area, then this formula does apply fairly directly without area being included. And so going through these calculations, we find that X equals 9 and Y equals 9. So the location then of the centroid is about here, 9, 9. We also note that we have 1,000 pounds applied, and so somehow we need to determine the bolt loads, the fastener loads due to this load applied. So we can move this 1,000 pounds straight into this location, but this causes a moment as well. And so that should be considered in the calculation. Now, you can see here the distance in the y direction between this load and this centroid is about 5. And so 5 times 1,000 gives you the moment due to this load applied. So that allows you to represent the system as 1,000 pounds and 5,000 pounds per inch in this manner. It simplifies the problem a bit. Now we have the situation that we would like to calculate the distance between the centroid and each of these fasteners. So that is the next step. I know the coordinates. So that's a very straightforward calculation. And I can find the distance of all fasteners, which is 126 squared. So here we have the calculation that needs to be done. In the x direction, we have the force. So we have the moment times applied at the centroid times the distance to a fastener, and then that's summation over all the fasteners, the distance to all the fasteners. So that's 126, that's 5,000, and the distance between the moment applied and fastener number one is really 3. So that will give me a direction, the force direction due to for fastener 1 of 119.04. In the y direction, I have the moment applied again times the distance in the x direction due to the fastener, the distance between the fastener and the point of moment application. That's 3 minus 9. The moment is 5,000 pounds inch. And then the total distance area, the total distance squared of all the fasteners to the center is 126. So in this calculation, I'm able to then find the force in the y direction is 238.1. I also have the fact that there's a shear load applied. And you can see here the shear load applies only applied in the x direction, in this direction. And there's 1,000 pounds divided by 3 bolts. That gives me 333.3 for each of these bolts. And so then I can calculate the shear load for PX of 452. I can repeat the calculations for fastener 2. And feel free to pause the video and go through that calculation to make sure it makes sense. And to calculate fastener forces for fastener 2 in the x and y direction, again, in the x direction, you have 1,000 pounds divided by 3 bolts gives you 333. So we're after the force in the x direction caused by this moment. And how do I do that? I know the moment applies 5,000 pounds, but I want to calculate the distance for fastener 2 between here and this point. And so that distance in the y direction is really 6. And so that's why you have a 6 here. The distance squared from all the fasteners to the center is 126. So then I get the force reacted by fastener 2 in the x direction is 238. I can repeat the process for the y direction. You can see here that the moment applies 5,000. The distance for the fastener in the x direction is 0. You can see that they're aligned. So 9 minus 9 is 0, divided by 126. And then the direction of the force in the y direction in that fastener is 0. So I can calculate then the shear load due to the shear only and the moment also as well. Fastener 3, very similar calculation. Please pause the video and see if you can figure out how this was done. Congratulations for being able to figure out how it's done. And hopefully you can see the solution here and work it through, but it's the same process that was discussed. So then here we have the fastener number 1 with a load X that was found, the load Y that was found. For each of these bolts, we've done this. Note that when we add the X direction, we get 1,000, which should be because the 1,000-pound load should be balanced by these 3 bolts. But we also notice here that some bolts carry less than the others. For example, these 2 bolts are closer to the line of action of this load, so they, according to these calculations, these 2 bolts carry the most, while this bolt carries the least in the X direction. In the Y direction, due to this moment being applied, you can see that you do have a load of 238.1. In one direction is acting opposite from the other, but the summation of these forces is 0 since there's no force applied in the y direction. But these forces do balance this force being applied. So in the aerospace applications world, we use NASA standard 5020A. We'll be discussing 5020 today. These are the requirements for threaded fastening systems in spaceflight hardware. And there is a new version 5020A that I recommend that you go through. But today we'll be discussing 5020, NASA 5020. NASA 5020 is going to go through strength requirements, is going to specify factors of safety, ultimate design loads that should be considered. And typically in these calculations, the ultimate design load for P is calculated by including something called a fitting factor. And the safety factor is applied, and then you have the limit load applied. But the fitting factor is something that has been used in industry, typically of 1.15, that could help account for some misalignments or non-uniformities because not all bolts are engaged at the same time, or there are some situations with misalignments as discussed. We also can calculate it for yield design loads, so we'll use a yield factor safety instead. And notice that we want to do these calculations for the worst case combination of loads and environments. Joint separation is another one that we had discussed earlier. Ideally, we don't want to have a joint separation issue, and so factor safety is typically applied to prevent that from happening. We also include a fitting factor sometimes to make these joint calculations a little bit better. But we want to make sure that these mechanical joints using threaded fastening systems can withstand the design separation and ensuring that we're accounting for maximum, minimum temperatures, that we're using the minimum separation safety factor. And that minimum separation safety factor can be defined in this figure, as you can see, and can help us determine what kind of separation factor do I want to apply to my joint. If you don't have a critical separation, critical joint, then a factor 1 is sufficient. If you do have it, you want to examine, can this be catastrophic to the mission? And if it is, it's a 1.4, and if it's not, 1.2. Locking features need to be considered because in many cases in spaceflight hardware, we can have a situation where the threads or the nuts can come apart due to vibrations. So we typically want to add a minimum of one locking feature that does not depend upon the preload in order for the fastener to function. Devices such as jam nuts are not typically recommended, but there are other ways to apply a locking feature, and they're described in FAA dual locking devices and fasteners, but we've seen them in other documents in what needs to be done. We have discussed the dimensional considerations in selecting fastening hardware. This was discussed earlier, so I will not spend a lot of time on this. We want to make sure that the margin of safety is greater or equal to 0, including a fitting factor, a safety factor, and then we want to make sure that we have the allowable of that fastener included in the calculation. It's also important to consider nominal, maximum, and minimum preloads. We have to address for those because you could have those situations, and you could have a potential for relaxation of that preload, creep, and then perhaps the temperatures can affect the maximum and minimum expected preloads. And so it is important to adjust for those situations. Typically, adjustments are applied for various situations. Like I said, creep, short-term relaxation, typically due to imperfectly matched surfaces. You could also have a change of preload due to the temperature differences, and it can be from a various number of sources. We can apply adjustment of 5% for initial preloads for joints when it's all metallic, and it is useful for short-term relaxation. We can also calculate the maximum expected preload loss from creep if possible. It's not always easy to find, but you could estimate it based on any test data you may have. And so the maximum initial preload for strength and fatigue analysis should be considered in any of these calculations. And that includes gamma, which is a preload variation. We want to consider sigma max, Cmax here, which is a factor that accounts for the maximum value of the control installation parameter. And so you can then calculate an effective torque that is specified for the hardware. And then use that in your preload calculations to ensure that we do not have a problem in the design. For separation analysis of separation critical joints and for fatigue analysis, the minimum initial preload should be considered. And again, Cmin here is a factor that accounts for the minimum value of control installation. For example, if the torque control is used, then effective torque could be 40 plus minus 2, then C minimum here becomes 40 minus 2 divided by 40, or 0.95. So that becomes a coefficient to this formula for minimum preload. For the use for using joint slip analysis and separation analysis of joints that are not separation critical, the minimum initial preload can be considered. We also have to calculate the ultimate strength analysis for shear loading. And for shear loading, this is the typical calculations that will need to account that will be needed to account for. Now, it is important to understand that for fasteners, they're on the simultaneous application of tensile and shear loads. We want to make sure that the system can survive these interactions. And preload is typically omitted from these calculations. The interaction equations are given here, and they're given for two situations when not accounting for plastic bending or accounting for plastic bending. We also have the relationship of minimum preload and torque, and these are the formulas we had discussed before. Here's some nut factors K, which said that we talked about using as 0.2, but if they're given or measured, you could use them from a table. We also have the preloaded joint analysis methodology, which is a NASA Tech Memo 106943, fairly consistent with the NASA 5020. We also have another one called Criteria for Preloaded Bolts. That one was released in July 6, 1998. My point is that you're going to find in the literature various sources on how to deal with preloaded bolted joints. So the failure modes in general will be shear frictions, gapping, tension failure of the bolt, shear pull-out of the threads, and shear failure of the bolt. That's for the bolt specifically, but you also want to consider the membrane behavior. And again, here we're showing how to account for the effects of minimum and maximum preload. In your calculation, you can have preload loss up to 5%, and then you're going to have the preload loss due to thermal that should be considered, and the preload uncertainty, depending upon the technique that is used in the measurement phase. So bolt tension failure, the first step is to calculate the total bolt load PB. So you have a load P that's acting externally to the joint. You want to calculate the load that goes into the bolt, and that load is going to be preload plus the factor of safety times external load times the joint efficiency factor C, where C was earlier discussed as the bending or the stiffness of the bolt divided by the stiffness of the bolt plus the stiffness of the members that this bolt is attaching. You can then use these calculations to guide you into determining the minimum cross-section of the bolt based on these margin calculations. You can also do it for shear pull-out of the threads. So slippage is not always considered critical. It may be more critical for precision type structures, but its criticality depends a lot on the application. And the shear friction slippage equations are provided here. Note that the coefficient of friction will have to be known for this calculation to work. The important thing is that we have the minimum preload minus the external load times the coefficient of friction. That's your shear load allowable that will be used here in the margin safety calculation. Gapping is something we had discussed earlier. This is the formula that needs to be used for the margin calculation. Here's some kind of top-level view of lessons learned from the NASA NESC course on bolted joints and some preview material from Instar Engineering relative to bolted joint designs. So here we continue with why it's important to look at these standards. And the reasons we have had failures in 1996, primarily due to the locking feature not being used, and a small screw backed out and jammed a gear in an external airlock, preventing the astronauts from being able to open the hatch and then performing operations, EVA operations. ISS Flight 12A also had almost a loss of mission due to a bolt issue. We've also had issues with the space shuttle antenna with bolt issues that had locking feature issues. This is kind of like a summary of issues that were found of the Skylab threaded fastener failures, and there's about 80 fastener issues, and they're all recorded in multiple sources. But in general, we have a combination of inadequate design, improper assembly, excess or insufficient torque, damage in handling, and then poor manufacture or faulty parts. General requirements for fasteners were discussed earlier, but this is kind of like a summary of those. We want to make sure we have adequate structural strength, adequate life, adequate joint separation factor safety, so we don't have a leakage that could be detrimental. Incorporating locking features is of extreme importance. Guidance on the selection of fitting factors, which we recommend 1.15, and those account. A fitting factor helps you to account for misalignments. Not every bolt may be in contact at the same time, and so you may want to include a fitting factor for that. You have a low risk approach for fatigue life, typically, if you're using the right bolts. Specs for joint separation factors of safety should be talked about, locking features, and then really implementing a good fastening system control plan that ensures that no FOD is introduced into the manufacturing. There is a whole area of fracture control and fatigue. All fastening systems have to meet the service life definition without fatiguing and fracturing. One can typically verify these specs of fatigue and fracture against NASA 1519 or some fatigue testing. But there are approaches that allow you to consider it to be low risk. If you're using threads, as we had discussed earlier, They're fatigue resistant as UNJ, UNR, MJ, and are used in joints containing non-metallic clamp materials and satisfy a good separation criteria. You could find ways of not having to directly comply with fatigue failure requirements, although you will meet the intent through meeting these three things here. Fracture control has always been a very important aspect, but it is not really required to perform a fracture fatigue analysis. Fastener life requirements exist for NASA. They usually come from NASA standard 5001A. And fastener fatigue and fracture requirements have existed previously, and everybody treats them differently. But the important thing to note is that no analysis is really required for those. The design separation factor safety is important. It was discussed earlier to ensure that there's no issues with the joint relative to leakage or some other fatal mode of concern. Separation at the joint can also cause excessive bending and potential bolt rupture. Locking features are very important regardless of preload. This was discussed earlier. Safety wires are typical approaches for locking features. Liquid locking compounds and other adhesives have been used for locking features. And you can do torque measurements of witness coupons to ensure that that the processes are robust. Design requirements for materials are of extreme importance, and they're covered in NASA Standard 6016. You also have to really have good configuration control of lubricants, coatings, sealants, and locking features. Analysis criteria typically looks at tensile loading, shear loading, and interaction of tension, shear, and bending, nominal, maximum, minimum preloads, using the right kinds of knot factors. They're substantiated by test, strength or yield criteria, shear loading like a joint slip analysis, and a joint separation analysis. There are several case studies demonstrating that, you could have an issue with the system, and so it's important to understand that um, there's some typical guidance that should be followed, and that's that we want to make sure that we have a good understanding of the initial preload. And that should be substantiated by some sort of amount of testing that allows you to gain confidence in those torques. We also think it's important to look at installation removal if you're going to be reusing hardware, um, and it's not separation critical. You can determine preload variations using test statistics. Here's an example of a lot of preload and tension and torque variability. And so there are approaches that people have used in establishing 1995 tolerance limits on the preload with measurements of the standard deviation and so forth. So that is an approach that people have used to kind of create bounds on what is acceptable for preload. Separation before rupture should be considered. I invite you to pause the video and look through this flow chart. But in general, we want to make sure that we can follow a methodology to determine whether joint separation could happen before rupture as an alternative to detailed joint analysis or testing. And if separation will occur before rupture, then you should perform analysis according to certain sections. But if rupture will occur before separation, then you have to perform analysis according to a different section. And those are provided here. People have done a lot of shear testing interaction Here are some photos showing the interactions between tension and shear using this fixturing. And people have shown that the shear tension interaction generally follows a pretty good curve like this. You can see here the preload had very little effect in the test data. Here as well, shear tension interaction through the body. Here, you may not have had a good curve fit. It was not perfect, but my Benken squared, it got a little bit better. But you still have faders that happen inside the curve that we're looking at. Again, preload has very little effect. So another one is to use 2.5 and 1.5. Not too bad. 1.2 and 2. But regardless of the formula you use, you want to have a good understanding of how that curve compares to the problem at hand. So this through the body, and then this through the threads. Detrimental yielding also should be guarded against, and you can determine that by making sure you're not affecting fit, form, and function or integrity of the hardware. And in many cases, fastener yielding is not a problem. Joint separation is of extreme importance. It was discussed earlier. So it's important that for a joint to maintain a good seating performance, and we don't want to have an issue where you have a leak rate that's unacceptable. And the analysis should be done with the minimum preload. Joint slip is another kind of analysis that should be performed. And the idea is to, and if you're going to rely on friction, we want to be careful because the friction coefficients may not be well established. But in many cases, we want to require positive margins of safety for ultimate design without having to rely on the friction. And if you were to consider it, you should not consider coefficient friction greater than 0.2 for clean uncoated surfaces like metal surfaces and 0.1 as an example, unless you have something that will be based on test. I also encourage you to go through the Parker O-ring handbook to learn more about seals and O-ring performance, and also seal design guides by Apple Rubber. I think these two sources are of extreme importance in the analysis of seals, and so I invite you to go through those materials because they play an important role in pressure vessel design that include flanges and bolted joints with for example, a O-ring or a seal.